السلام عليكم دكتور.
وعليكم السلام.
بس عندي إذا ممكن اقتراح إن الكويز القادم هل ينفع يتأجل لليوم اللي بعده الخميس بدل الربوع، لأن يوم الأربعاء في mid term ICS.
We don't have class on Thursday.
Yeah. يعني to come out of class quiz.
I don't think it's acceptable by everyone. Just give me the approval of everyone. I'm okay with it.
Okay. So
Okay.
it's possible to have a vote for it?
No, not a vote. It has to be unanimous. Everyone has to agree, because bringing everyone outside the class time, it's not something that I want. It's not something that we should do unless everybody agrees on that. And that's what we did when we changed the class time.
Can you make
How about
هل تقدر تسويها نفس النظام؟
Let's get started شباب. It's 10:22. We can postpone the discussion until the end of the class. Okay. طيب, بسم الله الرحمن الرحيم. Welcome to Ch4.1. So today is our 14th lecture. And in today's lecture, we're going to continue talking about, we're going to continue with chapter 4. We're going to cover 2 more interesting topics on chapter 4. But before that, just a few announcements. So homework 2 is posted, and inshallah, let's do this Thursday at 11:59 p.m. To submit the homework, please use a Periscope, and also quiz 3 is on Wednesday. And quiz 3 on Wednesday, and it's going to be during the class time. The material for quiz 3 is what we've covered last week, meaning that chapter section 4.5, which is the mesh analysis, along with its special cases, as well as the Thevenin and source transformation and Thevenin and Norton equivalent circuits. Okay, so let's go over what we did last time. So if you recall from last lecture, we studied Thevenin and Norton equivalent circuits. We had a way of classifying problems into multiple categories, depending on the fact. We had a way to classify the approach of finding the Thevenin resistance into two main classes. One with independent sources only, and the other one is with when we include dependent sources. But the overall picture, the overall thing that we're trying to achieve, we have a big circuit, and we want to simplify it with a voltage source in series with a resistor, and that's what we call Thevenin equivalent circuit, or a current source in parallel with the resistor, and that's what we call a Norton equivalent circuit. So we have Thevenin equivalent voltage source in series with a resistor, and you can use source transformation to move between Thevenin and Norton equivalent circuit. And if you recall, in Norton equivalent circuit, we have I short circuit, R Thevenin, and this one is called Norton equivalent circuit. So I short circuit is related to phi Thevenin by this relation. And in this lecture, we're going to see one of the applications of Thevenin equivalent resistance. In particular, we're interested in the maximum power transfer to load. Ziad?
When we have no dependent sources, the Thevenin voltage would be 0, and so also the short circuit current, right?
When we have no independent sources, we will have a 0, meaning that phi Thevenin will be short circuit, I Norton will be open circuit. So, yes. So
and if we want to, we will still have to find the resistance. But if you want to draw it, do we draw it like this with the source or without?
No, we draw it without the source. You're saying that it's a short circuit at the end of the day. Or you draw it with a source with 0 volts.
Okay.
So we'll take one of the applications of one of the applications of Thevenin and Norton equivalence, and this is known as maximum power transfer. So in many cases, you're trying to you have a circuit, and you want to find the conditions under which you can maximize the power transfer to the circuit. Let's imagine that you have a generator, and that generator is generating electric energy, and you connect your circuit to that generator. So in theory, you would assume that, well, I should have the maximum, I should have all of the generated power is actually being used by the device that I'm using. But the reality is not. Meaning that because the generator usually has some non-ideality, it has some internal resistance, you will end up not absorbing all the power generated by your generator. So you're interested in maximizing something here. You would say, like, how to maximize it. So that resistor, that generator, has specific resistance, specific internal resistance. It's there. I cannot do anything about it. What I can do is I can design my device such that I maximize the efficiency. So what do we mean by efficiency? Efficiency is something defined like this. I need the power dissipated divided by the power generated multiplied by 100%. This is the efficiency. This is one of the definitions of efficiency. So meaning that I want to maximize, I want to get as much out of the generated power as possible. So I want to design my system. I want to design my device based on that. So in order to design my device such that I can meet this condition, I need to know the Thevenin or Norton equivalent circuit of that generator. And we will see why in a moment. So this is one of the applications. Let me call this application 1. Application 2 is actually is very important. If you look into, if you're trying to transmit a communication signal, if you're transmitting like bits from one point in space to another, you won't believe how much power you are transmitting. Actually, it's, for example, you're pumping 1 watt, you're getting 10 to the negative 12 watts or something, and in a very short distance, a very relatively short distance. So your goal here is, okay, how would I design the receiver such that, or how would I design the receiver? The receiver will be connected to an antenna. How would I design the receiver such that I can absorb as much power as possible? So what impact does this have into our system is that it will increase something called signal to noise ratio. What do we mean by that? So in any real system, you have a signal, the thing that you want to communicate, and this affected by noise. Noise could be another transmitter is transmitting in the proximity, and this is going to interfere with your system. It could be your hardware is generating some heat, and this can affect the performance of your system. It could be something like, in very sensitive systems, it could be the light, the fluorescent light, so they generate some noise that affecting your system. So your goal here is to maximize the amount of energy that you capture from the received signal. So you want to maximize something called signal to noise ratio. So this is defined as power of the signal divided by power of the noise. So this is one of the applications of, this is why we are interested in the maximum power analysis. And in many cases, or all of these cases, we need to revert to a Thevenin equivalent circuit, because Thevenin equivalent circuit will give us a model for the, say, like the generator, and we can design our system accordingly. So you might ask yourself, okay, I'm interested in the maximum power transfer to a load. So what is the condition for this maximum power? And the answer to that, let's derive it. So let's assume we have found the Thevenin equivalent circuit. So we have a big circuit, and say like this is the generator circuit, and we found the Thevenin equivalent circuit for that. This was A, this is B. So we found V Thevenin and R Thevenin. So now let's connect a load to this circuit. So now the load has a resistance of RL. So the resistance of the load, I modeled my load, I modeled my device as something with a resistance of RL. So let me bring this one here, copy it, paste it. And connect my load here. So let me now find the current. So what is IL? So I can find IL, but before that, let me find, or I can find IL to find the power dissipated by, or the power delivered to the load. So the power delivered to the load is given by the following. Okay. To the load is the following. So let me use the particular for that. So P will be I square RL, and I square is by Ohm's law is actually V Thevenin divided by R Thevenin plus RL multiplied squared multiplied by RL. Okay, this seems straightforward here, so we did not do anything fancy. All what we did was we tried to find the expression of the power delivered to the load. So we found the Thevenin equivalent circuit of our system. Then we connected the load and tried to find the maximum or the power delivered to the load. So from calculus, if I know an expression, so like this, if I want to find the maximum, or if I want to find the maximum, then I need to take the derivative of P. If I want to find the maximum power transfer to the load with respect to the value of the load resistance, then I need to take the derivative of the power with respect to RL. So let us find RL that maximizes this. So we know that in order to do that, you need to find dP by dRL and set it to 0. That's what you need to find. So if I differentiate the power with respect to load resistance and set it to be 0, then in this case I will end up with RL plus R7 squared minus RL multiplied by 2 RL plus R7. And this is all divided by RL plus R7 to the power 4. So in order to maximize it, in order to set it to 0, I need to set the numerator to 0. So this could happen if I expand the expression, then I will get RL squared RL R7 plus R7 squared. So this comes from the first term. Then from the second term, I will have minus 2RL minus 2RL R7 equals to 0. So in this case, I have some cancellation here. So this will cancel with this. I should have
Mr. It's
RL squared.
2RL square.
Okay, 2RL squared. So in this case, I will have the following. RL squared equals to R7 squared. So this implies that RL must be equal to R7. So the condition for the maximum power delivered to the load or transferred to the load is if the load resistance is equal to the Thevenin resistance. So if I know the Thevenin resistance of circuits and I want to design a load to maximize the power transfer to that load, then I need to set the impedance or the resistance of my load to be equal to R7. Very interesting. Now, what will be the maximum power in this case? So I need to go and substitute. So if RL equals to R7, then from the power expression, I will get phi Thevenin squared divided by R7 plus RL, which is in this case R7. So I will have 2 R7 squared, which means 4. And there will be RL, which is again R7, and there will be some cancellation. So I will end up with the following expression. So this comes from this expression. Then if I simplify it, I will get phi Thevenin squared divided by 4 R7. So let's summarize. So the condition for the maximum power occurs when the load resistance is equal to the Thevenin resistance, and the maximum power occurs when or the maximum power is given by this formula. Note that in this case, let me correct it here. So it should be R7, which is again R7 equals to R1. So here, notice that this equation is only valid if and only if RL equals to R7. So if RL is different from R7, then you need to use the standard way of finding power, not this equation. So again, this equation is valid if and only if RL equals to R7. Any question about? Okay. So yes, Ibrahim.
Doctor, what if we know the value of RL and we can model the generator or the supplier to model the R Thevenin to equal RL? Is that a bit?
The thing is, like, this is something usually we don't have control over. So this is something out of our hand. For example, the generator could be anything like, for example, a battery. So if you, I mean, can you design your own battery? You need to build some sort of facilities to support this manufacturing process. But it's much easier to more financially or cheaper to buy it from the market and work on something that you can control. Okay. عبد الإله.
ايه دكتور،
Yes.
الحين ال RL وال RH دائما يكونون in series ولا في حالات يصيرون في parallel؟
No, if we're talking about the Thevenin equivalent resistance, they have to be in series.
يعني دائما نحط لود لهذا Thevenin resistance يكونون في series.
Yes. If we're using the Thevenin equivalent circuit, if we're using Norton equivalent circuit, then you have the load to be in parallel with the Thevenin resistance.
تمام.
Good. Okay. Muhannad.
So, Doctor, if we calculated and found that out that our load doesn't equal R Thevenin, can we just add another resistor in series so they will be equal?
That's one of the things that you can do, but the issue with this one, it's doable if RL is less than R Thevenin. But here the thing is, like, you can design your system to have more resistance in your case, but the issue is when it's less than when it's less than R Thevenin. There are multiple ways to get around this problem. It's not something that's okay. That's there. You can do anything about it. But there are multiple ways to get around this problem. Especially we'll see. I don't know if we're going to see it in this course, but usually this is not the case. The case is like we have a resistor in series with a capacitor or inductor, and we can kind of like add some sort of capacitance or inductance to cancel one of them, so you can maximize the power. But there are multiple ways of dealing with this issue. What you said makes sense. If the Thevenin resistance is less than or greater than the load resistance. But again, the resistor that you add, unless it's added to your load, it's not going to be helpful for you. Meaning that if what you're talking about is something like how to say that? If what you're talking about is you're adding just a resistance to maximize the power transfer to the load, usually this is not going to be helpful for you unless this added resistance is part of your load. Okay, so let's take an exercise here. We have the following circuit, and we have a load resistance, and we want to find the value of RL that results in a maximum power transfer to RL. Then once we find this, we need to find the maximum power, and then we need to find the percentage of the energy. Okay. Before we start, I just want to point this out. So the very first thing that we need to do is actually, because this is our load, we need to disconnect this load. So if we disconnect this load, then we can start solving this problem. Right. Okay. Let's see who's gonna. Walid.
Yes, Dixon.
Okay, let's go ahead.
We first find the V-Thevenin,
Yes,
which we can find it by using VDL.
exactly. So let me just Walid, let me just draw the circle so we can.
Okay, take it.
But this is 150. Okay. Okay, you're saying what? What is V-Thevenin?
V-Thevenin equal 150 over 180 multiplied by 360.
Exactly. Divided by 360, and this is going to give me 300 volts. Okay, this is V-Thevenin. Wael?
Yes. Now we can find the equivalent resistance.
Okay, so what is
We
R?
first deactivate the voltage source.
Yes. So
and then find
let me
the
draw it. Okay.
and then find the sum of the resistance.
Is
They are
this
in parallel.
Okay, they are in parallel.
Yeah.
Okay, very good. So R-Thevenin will be something like this. So it will be 30 parallel with 150. And this is going to give me 25 ohm. So if I draw the circuit, it's going to be something like this. So here 300 volts. So let me give myself enough space. 300 volts. Then I have 25 ohms. Then now I can bring back the load resistance. Okay. So this is not it. I was asked to find RL. So what is RL, Ahmed Al-Hamid?
RL is equal to R thickener, which is 25.
Exactly. RL equals to R-Thevenin, which is 25 ohm. So the value of RL that maximizes the power transfer to the load is actually R-Thevenin, which is in this case 25 ohm. So if I have 25 ohm, I will have a maximum power. I will guarantee that the maximum power is transferred to the load. Now, the second part is asking me what is the maximum power, not the resistance, but what is the maximum power? Let's see, Salman. So what is the maximum power?
Power equal to V-Thevenin square over 4 L, which is 300 square over 4 multiplied by 25.
Okay. 4 multiplied by 25, which is in this case 100. So this is going to give me 900 watts. Again, should be, there's a typo. This one should be R-Thevenin as RL. Okay. So let's see. The second or the third part is asking us what is. So now we set RL to be equal to R-Thevenin, so we ensure that the maximum power is transferred to the load. So what percentage of the power delivered by a 360 volt source reaches RL? In this case, okay, Abdullah Al-Jariri, what do you think? What's the best way to approach this problem?
I think we should find voltage A and B first.
We found A and B, VAB, which is V Thevenin in this case.
And then we find the current. The voltage source.
We can find the current of what?
The current source of the
Okay.
voltage source.
Okay, so we need to find the current of the voltage source. So if we know the current of the voltage source, we can find the power. So let me do the following. So let me assume that I have, this is the current I, this is the current IS, and in this case, I need to find the current IS to find. I'm sorry. What you said is correct. So we need to find VAB. So what is VAB? Let me go back to Abdullah. So VAB is what?
300 over 50 times 25.
Exactly. 300 over 50 times 25. Exactly. So VAB, you can say that I, which is 300 times 50 multiplied by 25. And this is going to give me 6 multiplied by 25, which is 150 volts. Now, if I know VAB, this is 150 volts. So how to find IS? So let me look for a new name. Type. Okay, while.
Yes, I think we can get the voltage across the 13 resistance.
Okay, yes, and apply Ohm's law. So in this case, we get 360 minus 150 divided by 30, and this is going to give me 7 amperes. So now if I know that the voltage or the current is 7 amperes, so I know the power, I can easily find the power. So it's going to be 7 multiplied by 360, and in this case it's going to give me minus 2520 watts. So the percentage will be 900 divided by absolute value of multiplied by 100, and this is 35.17%. So you can see here that only 35% of the power generated by the voltage source is being absorbed or is being dissipated in the source. Ahmed al-Nafi?
Doctor, doesn't V Thevenin equal VAB because those are in parallel?
No. So this is A, this is B. So V Thevenin is actually, what you can do is you can see that by voltage divider law, VAB is RL divided by RL plus 25 multiplied by 300.
Thanks.
Okay, now let's move on to the other exercise. In this case, we have a variable resistor, R0. And what we want here is we want to adjust it to ensure that maximum power is transferred to the load. So in this case, usually the first approach is to find the Thevenin equivalent resistors. So let me draw the circuit first. I have 2.4 kilo ohm. So I removed R naught in this case and tried to find the Thevenin equivalent circuit between A and B. Okay. طيب. Yasser. Okay, hold on, Yasser. So what should you do first?
Yeah, first we need to find P Thevenin. We can use any method. Any method.
What do you suggest?
Here, I would suggest mesh because we have a super mesh.
Okay, this is a good exercise, or this is a good suggestion. I would suggest something else. I would suggest applying source transformation to the 60 volt, and let's see what happens.
Okay, we can do that.
So I have 60 volts in series with 2.4. So let me do the calculation for you. It's 2.5. It's 25. Then you have 2.4 here, kilo ohm. And the other resistor is 4.8. Then you have a current source, 15 milliampere. Then you have 1.6 kilo ohm. Then you have 5 kilo ohm. This is A. Then I think here 1.8 kilo ohm. This is B. So you can see here that if I use source transformation, I have this one in parallel with that one. I have two current sources in parallel. So I can add them up. So I can simplify them to something, I can simplify the entire circuit to something like this. So the parallel combination of 2.4 and 4.8 is 1.6. I have 1.6 kilo ohm here, 5 kilo ohm here, and 1.8 kilo ohm here. So now if I want to find V Thevenin, what should I do? Okay, let's see. Rahim?
I think we should apply source transformation again.
Not really. We can do that. It's doable. But you can apply here a current divider law to find I2 or I. Yeah, let me call this one I2. To find I2. And this is going to give you 1.6 kilo ohm divided by 1.6 plus 5 plus 1.8, which is 10 kilo ohm, multiplied by 10 milliampere. And this is going to give you 1.6 milliampere. So now you know the current passing through the 5 kilo ohm resistor. So you can find the voltage, which is in this case the Thevenin voltage. Divided by 5 kilo ohm, and this is going to give you 8 volts. Okay, Thevenin equivalent voltage is 8 volts. What about Thevenin resistance? Okay, Hadi?
Deactivate the independent sources.
Okay. You can go back to the original circuit, or what else? You can directly work with this one.
Okay.
In this case, it's easier. So So if you directly work with this one, what should you get? So you
deactivate it, replace the current source with a short circuit, or
no,
without a wire, I mean.
It's an open circuit.
Yes, open circuit. And then just add the series resistor and the parallel resistor.
Okay. So in this case, we will have 5 kilo ohm in parallel with a series combination of 1.6 plus 1.6 plus 1.8. So let me cut it here. This will give me enough space. R equals to 5 kilo in parallel with 1.6 kilo plus 1.6 kilo plus 1.8 kilo, and this is going to give me 2.5 kilo ohm. So this is the Thevenin resistance. So the maximum power, the maximum, or the resistor, the value of the resistance that ensures maximum power transfer to the load is what, 12. Is going to be 2.5 kilo. Okay, very good. So now we found R naught, what will be the maximum power that can be delivered to R naught. This is straightforward. So it's a direct substitution of the equation. So P will be P Thevenin squared, which is 8, divided by 4 multiplied by R Thevenin, which is in this case 2.5 K, and in this case the maximum power is 6.4 milliwatts. Any questions, Shabab? Salman?
Doctor, in the previous slide, R naught, there is a little arrow. What does that mean?
It's a variable, meaning that you have the ability to adjust its value. So what happens is that you have the following circuit, and then you keep like adjusting the value until you ensure that we have the maximum power. So if you have a resistor with an arrow crossing it like this, it means it's a variable resistor. Okay? I assume the creed.
Doctor, does if the current source that I have is in series with RL, like I'm gonna like put it.
The current source you have in series. No.
What should I do in this case?
You mean like you have a current source here?
Exactly, yes.
So in this case, you know the power dissipated in RL. So our calculation doesn't make any sense to you. Because you know the current passing through RL.
Yeah, okay, please.
Okay, so let's move on to the following exercise. This is one of the most interesting exercises that I've come through and I've come across in this course. So what we have here, we have a circuit with the 30-volt source, and for somehow we have the ability to adjust the generator. We have the ability to adjust the resistance of the generator here, which is R naught, which is the Thevenin resistance, basically. So we are asked to find what the value of the variable resistor R naught in the following circuit here that ensures that maximum power dissipation in the 6 ohm resistor. What do you think, Shabab? I need new names. Right. Okay. Okay. All of you have participated. Okay. طيب جانا واحد. طيب حمد سوالم.
Yes, I think it will be 6 ohm.
Why?
Because our Thevenin has to be equal to our load to generate the maximum power.
Okay, good. Ziad, do you agree with him?
Maybe it's multiplied by some factor like half, because it will change the.
Okay, good. Ibrahim, do you agree with both of them?
Yes.
Okay, good. Ahmed and Nafi, do you agree with both of them? With all of them?
Yeah, I do.
Okay. Wael?
No.
وش عندك؟
I think R0 or R0 should be 0.
Exactly. So R0 should be 0. To maximize the power dissipation, R0 should be 0, because you don't want here. This is the Thevenin resistance. So you don't want any power to be dissipated in the R0 here. So R0 should be 0 ohm. So in this case, the maximum power will be simply just 30 squared divided by RL, which is 6. In this case, it's going to be 150 watts. So this is a different problem, but this is an interesting problem. It says that, well, if we have, so the heading message here, it says that if we have a 0 resistance associated with the generator, in this case, with our source, any value of the load resistance will ensure that the maximum power is transferred to that load resistance. So it doesn't matter which value we use. So that's why it's always preferable to make sure that this, if we see like an ideal source, we always say that the ideal source has a series resistance of 0. And this is the reason behind this. Okay. Now let's discuss the last topic of chapter 4, and chapter 4 will be the last chapter that we discuss only. We only discuss the resistive circuits. So starting from chapter 6, we will not cover chapter 5. So starting from chapter 6, we're going to talk about inductive and capacitive circuits. We're going to talk about inductor and capacitor. In particular, before we conclude, it's very important to actually shed some light on this very interesting, very amazing topic. I'm saying amazing topic because it has some deep mathematical background or underlying concept that we need to emphasize. And the analysis that we're going to cover here is the concept behind it is not limited to this course. You're going to see it in too many courses, and one of the very fundamental course that you're going to see this concept is EE207, which is signals and systems. Okay. So let's talk about something called linear system. So what do we mean by a linear system? You may ask yourself, well, okay, first, what do you mean by a system? So what is, what's the definition of a system? So a system is a mathematical model, or a system is a linear, if it's governed by a linear operator. So what do we mean by a linear operator? I'm keeping like listing a definition after definition. So a linear operator, we'll define it in a moment, but let's take an example. If you have a function and multiply it by a constant. This is a linear operator. If you take a function integrated, this is a linear operator. If you take a function differentiated, this is a linear operator. So that's why, for example, if we're talking about current and voltage by applying Ohm's law, we see that we have a linear circuit, because if you take a current, multiply it by a constant, which is in this case resistance, you'll get the voltage. In the case of inductor, for example, we see it's a linear element. If you take an inductor, if you take the current passing through an inductor, you differentiate it, multiply it by a constant, you will get voltage, which is again still like a linear operator. A capacitor is also a linear element, linear circuit element. Why? Because if you take the current, passing through the capacitor, integrated, divided by a constant, you will get the voltage. Okay, so those are examples of multiplying a function by constant, integrating that function, differentiating this function, are all examples of linear operator. What about a nonlinear operator? You can multiply a function by a constant, then adding another constant. You can take square of a function. This is definitely a nonlinear operator. Linear systems, a system that poses that's linear is commonly used and has various applications in science and engineering. As a matter of fact, we always prefer to deal with linear system. So even if sometimes our system is non-linear, so we try to approximate it with a linear system. Okay, so that's enough about the background of linear systems and the difference between examples of linear systems. So let's define linear systems. So let me say I have a system here. And I take an input, X, apply it to the system. You will take an output. So let's take an example of a system that we're going to, we just saw. So let's go back and let's choose this circuit, for example. So what's the input in this case? If I say like RL in this case is say like 25, صح? Okay, 25. So the input here is the voltage source. So the voltage source is the input to our system. So I'm inputting a voltage source. The output of my system in this case is the voltage across RL. So the voltage across RL will be
150.
150. So yes, thank you. It will be 150. So the input. So we can think about the entire circuit here as a system. The input to the system is the voltage source. The output is the voltage across RL. So if the system is linear, then if you take x1, meaning that you take a value of the voltage source, you will get specific output here, y1. If you change the value of the voltage source, you'll get another output, y2. Okay, this makes sense. So in this case, instead of say like 360, you got for example, the input was 500, you should get a different output. You should get different VL. Now, what happens if you take an input that's equal to x1 plus x2? You take 360 plus 500. So you should get an output that's equal to the output in the case of 150, in the case of 360, and the output in the case of 500. Okay, so let's take a mathematical example here. This might be more illustrative. Okay. So let's assume that y equals to 2x, and I'm saying that this one is linear. Let's see what happens. If I choose x1 to be 2, then y1 will be 4. 2 multiplied by 2 is 4. If I choose x2 to be 4, for example, then y2 should be 8. 2 multiplied by 4 equals to 8. If I choose x3 to be 6, which is 2 plus 4, x1 plus x2, then I should get 6, which is 12, which is again 4 plus 8. So in this case, y1 plus y2, which is 8, which is 12. Now let's take a system that's not linear, for example, 2x plus 1. I'm saying that this one is not linear. So let me take x1 equals to 2. y1 should be 5. x2 equals to 4. Let me say y2 equals to, in this case, 9. So x3 will be 6 again, which is 2 plus 4. y3, in this case, will be 13, which is not equal to y1 plus y2, in this case 14. So you see that this is a linear, this is not linear. So how this is related to our circuit? So a linear source in this case is actually, if I'm trying to find the voltage and the current, and I'm trying to find them due to independent sources. Independent sources are kind of like linear input, and nonlinear ones are actually the dependent sources. So I cannot say like the contribution of the dependent source in case 1 plus the contribution of the dependent source in case 2 equals to the contribution of the dependent sources in both cases. So in this course, the circuits that we're going to deal are linear, meaning that the circuit that we're going to deal with are going to have a capacitor, inductor, and resistor, and those are linear elements. Contrary to our type of circuits that we're going to deal, if you're taking E203, for example, you see an operational amplifier, or you see a diode or transistor, and those are nonlinear circuit elements. So if we have multiple sources, say like I have a voltage source, another voltage source, a current source, the fact that I have linear circuit, it allows me to find the individual contribution of each one of them. So the resultant current, the current or the voltage, will be the summation of the contribution of each individual one. This is called the superposition principle. Meaning that if I find the contribution of, so if I say like I have 3 sources, I find the contribution, I find V1 let's go back here. So I have, in this case, maybe this is not a good example in this case. Let's see here. Okay. If I'm to find the voltage across R0 in this case, then I can see that the voltage across the voltage across R0 equals to the voltage across R0 due to only the 60 volt source plus the voltage across R0 due to only the 15 milliampere current source. So the contribution, the total contribution will be the contribution of the individual sources. And this is called the superposition principle. This technique might not be very useful when we're dealing with resistive circuit, but it's going to be very useful if we have different sources that are fundamentally different. For example, if you have an AC and DC sources. Okay. Now, how to apply superposition in our circuit? So what you need to do, you need first to deactivate all independent sources except one. So you deactivate all of them. Now you ask yourself, what happens if I have a bunch of independent sources and one dependent source? Then the answer to this is you deactivate all independent sources except one, and also you keep the dependent sources active. You do not deactivate the dependent sources. Then you need to find, once you deactivate all independent sources except one, then you need to find the voltage or the current that you are interested in due to only that source. Now you need to repeat the same step until you cover all sources. At the end of the day, you have you have multiple values of currents or voltages. Then you need to add them all up, and this will give you the contribution due to all of these sources. So this is where you add the individual contribution. So what if I ask you to find the power due to all sources? The answer in this case is you cannot apply superposition. So you cannot deactivate one source and find the power, then deactivate another source and find the power. No, because the relation between the power and the voltage, or the power and the current, is not linear. So what you should do here is you should find the current or the voltage due to all sources. You can add them up. Then at the end, you take this value, the added value, or the summation of all of them, and then find the power. Okay. This is equivalent to saying, for example, if I ask you to find the contribution, say, for example, you have an example of superposition. So you have a big tank, and you have two pumps that's trying to fill up the tank, and you want to find the contribution or how many cubic volume that pump 1 is going to add to the tank in a specific period of time, say like in 1 minute. So what should you do? The logical way is actually to stop pump 2 and just turn on pump 1, and after 1 minute you stop pump 1 and find the volume, the cubic volume of water in that tank. If I ask you to find, or if you are interested in finding the contribution of pump 2, then you should turn off pump 1, then turn on pump 2, make it run for 1 minute, then stop it and measure the cubic volume of the contribution of pump 2. So this is exactly what we're going to do. So let's take an exercise here. Let's find the currents I1, I2, and I3, and I4 using superposition. Here we have two sources. So clearly, since we are asked to find superposition, use superposition, so I need to activate one source at a time. So I have two sources. So let me start with. So let me start with the voltage source. So I'm assuming that the current source is not active. So let's deactivate the current source. So how to deactivate the current source? Karim?
Just put an open circuit?
Yes. We want to deactivate the current source. We replace it by an open circuit. Why? Because the current passing through an open, deactivating a source, meaning that zeroing the contribution of that source. So meaning we want to find, if we have a current source, we want to find the value of the current. That's, we want to make sure that the contribution, or we want to find the current of that current source is zero. And this could be done if we replace a current source with an open circuit. What if we have a voltage source? In this case, if we have a voltage source, then we need to replace it by a short circuit. Why? Because the voltage across the short circuit is actually zero. And in this case, the contribution of the voltage source, the voltage contribution of the voltage source is going to be zero. Okay, so let's activate. I'll have 120. Okay, so the current source is being deactivated, and in this case, it's replaced by an open circuit. So I need to find the currents I1, I2, I3, and I4. So if I go back to the original circuit, so I1 is this current. So I will call it I1 prime because this is I1 due to only one source. I2 is flowing this way. I3 is that way. I4 is this way. So clearly here, I3 equals to I4. But how to find I1, I2, and I3 in this case? So the multiple ways, Ibrahim.
Maybe we can use mesh current.
I think mesh current will give you two equations. Node
What about the node voltage?
Node voltage. So if you use the node voltage, you'll get V1 minus 120 divided by 6 plus V1 divided by 3 plus V1 divided by 6 equals to 0. So clearly V1 is 30 volts here. So now if I found V1, then I can easily find I1 prime. So in this case, I1 prime is going to be 120 minus 30 divided by 60. And this is going to give me 15 ampere. I2 prime.
By 6.
By 6, yes. I2 prime is simply V1 divided by 3, which is 10 ampere. I3 prime should be equal to I4 prime. And in this case, Hamidani?
I3 prime and I4 prime are equal with what?
Okay, we'll come to this. So what is the values here? So in this case, it's going to be 30 divided by 6 again here. So it's going to be 500. So now I found the contribution of all of them. The contribution or find the value of the current due to only the voltage source. So let's see what happens if we deactivate the current source. So what should we do? If we deactivate the voltage source, so what should we do here? Taziz?
Again, doctor, I didn't understand you.
Okay, so you raised your hand. Do you have a question or you want to contribute?
Yes, I had a question.
Okay, so we'll come to it. I need to solve this one before I run the time. We'll come to questions. Okay. Talal?
We add the short circuit.
Okay, so we replace the current, we replace the voltage source by. So first we bring back the current source, and we replace the voltage source with the with a short circuit. Let's now deactivate the voltage source. Okay, so this is okay. So now if I label all of those, this is I1 double prime, I2 double prime, I3 double prime, I4 double prime. So in this case, I have. So what should I do, Yasser?
Yes, we can use again the node voltage or the mesh.
Okay, exactly. Yeah, you can use either. Either one of them will give you the right answer. And again, in both cases, you can use any method that you want. Just a matter of which one will give you the fastest way of solving this problem. Maybe the difference in time is just 1 or 2 minutes. So if I solve for it, I'll get V2 equals to minus 24. Okay. Again, I'm not interested in V1 and V2. I'm interested in I1, I2, I3, and I4. So it can help me with I1, I2, I3, and I4. So let's start with I1. So I1 double, I need to look for new names. Okay. Ziad.
I1 is equal to minus V1 over 6.
Minus V1 divided by 6. V1 is negative, so it's going to be 12 divided by 6.
Oh, okay.
So it's going to be 2. Okay. I2 double prime. Let's see. Ahmed al-Nafi.
It will be V1 over 3.
It will be V1 over 3. V1 is negative 12. So I2 double prime will be V1 divided by 3. It's going to be minus 12 divided by 3, and this is going to give me minus 4 ampere. So I3 in this case, let's see. Muhannad?
It will be V1 minus V2 over 2.
Exactly. It will be V1 minus V2 divided by 2. And in this case, it's going to be 6 amperes. I4, in this case, I4 is not equal to I3. So, Ibrahim?
V2 over 4.
V2 divided by 4, and V2 is negative again. So V2 divided by 4, and in this case, it's going to be minus 6 amperes. So we're not done yet. So now I need to, in order to find I1, I2, I3, and I4, I need to add them up. So I1 prime plus I1 double prime, and this can give me 15 plus 2, 17 amperes. I2 should be I2 prime plus I2 double prime, and this is going to give me 10 minus 4, and this is going to give me 6 amperes. I3 will be I3 prime plus I3 double prime, and this is going to give me 5 plus 6, which is 11 amperes. I4 will be I4 prime plus I4 double prime, and this is going to give me 5 minus 6, and this is minus 1 ampere. Okay, that's it for today, and inshallah next lecture we're going to solve one more exercise on superposition. I'm not going to post the solution for this one. I want to solve it with you because there are some concepts associated with it, and then inshallah we'll start talking about capacitors and inductors. We'll start chapter 6. Okay, now back to Abdulaziz, your question.
Yes, doctor. So when we saw the circuit, you said that the best way to start with it to use the node voltage method.
Yes.
So is there a key that in each circuit to find out what's the best method to use?
When I say the best way, I'm saying like the fastest way, because here I need to solve one equation only. So I have two essential nodes here, right? So I have one of them as first one as a reference node, and the other one is actually the one that I'm going to. So I need to solve one system of one equation. So just how to know the difference between which method to use. This comes with the practice.
Mm-hmm. Okay.
And as a matter of fact, you can actually solve this one using, if you decided, well, I'm gonna solve it using Ohm's law or voltage and current divider law. What you can do is actually you can apply source transformation, then voltage and current division to get these values. So there are multiple ways of getting this problem. So this could be an exercise for you in order to ensure that you test your familiar with all method to get to try different methods to see which one will give you the correct or the fastest way of doing this problem.
Very clear. Thank you, doctor.
Okay, Ziad, yes.
Can you go to exercises before?
The one in maximum power transfer?
Yes.
This one?
Can you go to the next slide?
This one?
The next one. No, yes.
This, okay.
Yes. Here for the I2, we use the divider current, right?
Yes.
And so the 1.6 is the 10 kilo is supposed to be the R. What is it supposed to be to represent the
10 kilo is 1.6 plus 5 plus 1.8 plus 1.6. So the summation of all the resistors. Remember that for current divider law, the numerator is the resistor that we are not interested in, which is in this case 1.6, divided by the summation of all resistors, which is 1.6 plus 1.6. This is a 3.2. 3.2 plus 1.8. This is going to give you 5. 5 plus 5 is 10.
okay, but the one I use usually is the equivalent resistance over the resistance you want.
Okay, what you can do is if you say the equivalent resistance in this case, it's going to be 2.5 divided by 5 multiplied by 10. And in this case, 2.5 divided by 5. No. The equivalent should be, okay. Should be 1.6 in parallel with 1.6 plus 5 plus 1.8. So you should find the parallel combination and get. If you do that, you should get exactly the same answer.
Oh, okay. Yeah, because I got.
When you have two branches.
Oh, okay.
Or two resistors.
Oh, thank you. I got lost for a second there. Okay.
أيوة حسن.
ايوه دكتور، بس انا رسلت لك ايميل قبل يومين تقريبا، قلت لي اكلمك وقت على الساعه 12:30 تقريبا. في مجال اذا خلصوا الشباب اكلمك برايفتلي الحين ولا؟
Okay, can you call me 12:15?
اوكي.
Okay.
شكرا.